Okay. Yes. So today's speaker is Minjung Kim. Minjung got her bachelor's and master's degree at Inha University. I hope I pronounced that right. In Incheon, Korea. She then moved to Heidelberg, where she got her PhD earlier this year on the measurement of prompt and non-prompt J-psi production in proton-lead collisions at root S of 8.16 TeV with ALICE at the LHC. She has since moved to UC Berkeley, where she is a postdoc working on UPCs and ALICE and the EIC. And today she's going to tell us about quarkonium production and heavy ion collisions at the LHC.
Okay. Thank you very much for the invitation and also the introduction. Today I will talk about the quarkonium production in heavy ion collision at the LHC. So as you already know, the quarkonium refers to the particle with the quark and the antiquark bound state, as you can see in the left side. And it was from the 80s, it was really interesting, observable in these heavy ion collisions, since the idea of the quark-gluon plasma developed with the J-side production. Once this is pair inside the medium, then they cannot see directly anymore, but somehow blinded by the surrounding mediums with the color particle, like you can see on the right side. So this means that the production of J-psi is suppressed by the color screen in the QGP medium. And this can be naturally extend to the sequential mainstream scenario, which you already also know, I guess. The difference in the quarkonium binding energies, like the J-psi and the psi2s and so on, leads to the sequential melting with the increasing temperature or the increasing the energy density, as you can see on the left side in the cartoon. So which as a result, what we get as a probability of the J-psi production will be suppressed as the energy density gets higher. But at the LHC energy, this scheme is a bit changed. So with the large collision energy, the largest decibel cross-section production is expected. And actually, about the decibel produced per central plated collision is about 100, which is factor 10 times more than the RHIC energy. So which means that there is a chance to make a lot of J-psi, and also charmonium can be through the regeneration, which is taken place in the phase boundary or in the QGP, as you can see in the cartoon here. So once you have larger amount of the CC-BOT, then the abundance, it leads to have larger amount of the final state charmonium, and its charm hadron can be added. So this can be described in the similar plot you can see in the bottom panel here. So and also for the bottomonium, the LHC opened a new era for the bottomonium measurement as well. With increased collision energy, we could also obtain the larger BB-bar production cross-section, which allow us to assess the epsilon 1s, 2s, and also the 3s clearly. And this also the medium created at the LHC is hotter and longer, which means that the bottomonium can see the medium a bit longer and compared to the RHIC energy. So this gives us a chance or to provide a unique opportunity to use the bottomonium as a non-equilibrium proof of the full-time evolution of quark-gluon plasma. So at the LHC or experiment in general, the quarkonium measurement can be done with the S-wave quarkonium decaying into the dielectron pair. For instance, J-psi is decaying into electron and dielectron, and the muon for about 6% branching ratio, and the epsilon 1s is to dimuon is about 2.5%, which is quite substantial compared to the other heavy flavor hadrons. And also, what is nice at the LHC ring is that we have 4 main experiments covering the different kinematic range. For instance, in ALICE, we could cover the low PT and the mid rapidity and the forward rapidity with the muon arm, while the ATLAS and CMS cover the high PT range above 40, even 50, essentially. And also the LHCB participate in heavy ion physics, providing unique kinematic range from 2 to 4.5 rapidity window, which is actually really useful for the cold nuclear battery pack study, which we will see in the later slide. But it's not as simple as I explained so far, because we have to keep in mind for interpreting our measurement. First of all, there's significant and also PT-dependent feed-down contribution for the charmonium production and also bottomonium. To give you some idea, here I brought the low PTJ side and the high PTJ side production from different sources. The blue shows the direct contribution, while the green and gray-yellow shows the feed-down from the excited state, which contribute about 20 to 30%. And also for the charmonium, you have to consider the weak decay product from the multi-hadron. So situation is a bit complicated, and this ratio is not fixed, but also different for different states. So this I want you to keep in mind for the whole presentation today. But for the charmonium, at least we can separate the contribution from the multi-hadron based on the long lifetime of multi-hadron, separate statistically the prompt contribution, which includes the direct J-psi and the feed-down, from the non-prompt contribution, which decays from the multi-hadron. So today I will mainly play with show you the RAA and the V2. It's just a reminder, though you all know, I guess, the RAA or nuclear modification factor is defined as follows. The yield measured in the Large Hadron Collider is scaled by what is measured in PP, scaled by number of binary collision here for the hard probe. This basically quantifies the modification of the production with respect to the QCD vacuum. So if it's one, actually it's not there's no medium. It's not the no medium effect, but no effective medium effect, so that we cannot see anything through the RAA measurement. But if it's if you see some enhancements larger than one, you can say that there is some enhancement in the from the medium effect, and it's lower than one, as we know, or there's a jet quenching or something which suppresses the production of given particle. And the other observable which I want to show you today is elliptic flow V2. So in the non-central collision, in the as you can see in the left plot, due to the initial spatial anisotropy, in the end, you will get the momentum anisotropy of the particle emission through the rescattering in the medium. This can be delivered by the particle azimuth distribution, which can be written in this formula, and we take the second order Fourier coefficient to quantify this effect for each particle. So let me first start with the J-psi RAA, and here in the left plot you can see the DND atom measured with rapidity, and on the y-axis you can see the RAA, which is measured at Alice, which is shown in the red, and the blue measured in Phoenix. This, as you know, that the DND eta value is directly proportional to the energy density. So this plot really indicated how this different energy regime react acting on the J-psi production. So in the gold result in the 200 GeV, you can see the strong suppression toward the central collision, while you could see the increase of the RAA in the Alice measurement. But this is for the low PT, mainly from the 0 PT J-psi. But on the right side, you can see how it is for the high PT. So similar plot is presented here, but the J-psi is inside the window above 5 GeV, which is basically the high PT contribution. And the blue shows what we measure in the LATLAS CMS 2.76 GeV, and the red shows the star result. And here, what you can see is that the suppression increased toward the central events, but the size is more, the suppression size is more or less similar to each other in the star and the CMS. This already you can see that this kind of the hint of the jet quenching effect, but I'd like to discuss more detail in the later slide.
Can I ask you a question?
Yeah, sure.
Why is for the low PT at very small the charge the eta RAA larger than 1? Shouldn't this be 1?
You mean this?
No, to the left. The left
This
block
one.
is-
This can. There are several things which might influence. For instance, like we have low PT excess observed in the really peripheral collision. This can be also taken into account in this plot in particular, but.
How well do we know the number of collisions down there and the number of participants?
Yeah.
There's also photo production in that bed.
Yeah. Right. So
Photo production is so big.
yes, I can show you.
I don't know, I'm not sure what the PT cut is, but you know, LH has published results, RAA equals 7 for an appropriate cut with PT and.
All right.
So we don't have photo production for RHIC?
It would be this, it would be much less because the energy is lower.
That's why it's photo production.
But I mean, Star has, I don't know exactly what cuts, but I think Star has seen JSI photo production, but the cross section is much lower. So you're talking 3 GeV photons, and you're not that far from threshold.
So Minjung at the eta d eta equal to 1 is enhancement from 5 TeV data. Yeah.
You mean this one?
Right. So this is because
Yeah, this
when we compare it to right plotter, so that means
Right, this is-
the recombination is only happened at the low PT region. Is that right?
yes. This we can see more detail in the as a function of PT here.
Ah, you have
Yeah.
it. Okay. Thank you. Thank you.
So this is nice compilation plot obtained from Alice Atlas and CMS measurement as a function of PT in the mid rapidity. So as you can see here, the low PT is covered nicely by the Alice measurement, while the intermediate PT is covered by CMS, and the highest PT could be reached with Atlas detectors. I think nice. If we see the low PT in more detail, then we can study a bit more about this recombination effect. So this is the same plot as shown in the left side, but only for the up to 15 GeV. And the measured data is described by the statistical heterogeneization model, which is shown in the blue, and also the transport model, including the recombination effect as well. And but it's also interesting because their regeneration scheme is slightly different. For instance, transport model assume the continuous J-side dissociation and the regeneration through the QGP and the hadronic phase, while the statistical heterogeneization model somehow see the J-side production at the chemical freeze out in the phase boundary.
Before you move on, I'm just wondering, is this plot on the right actually consistent with the plot in the previous slide?
Yes.
1.4 plus minus.
I'm wondering about the same thing. I mean, it looks like it should be 1 instead of 1.5, right?
Yeah, but look, it comes, if you look at the error bars, it's, I don't know, 1.2 something, and the other one is 1.4. So it must be different.
Different.
So this is
Different
low
bidding.
multiplicity here. I'm confused, Barbara.
It should be- What I show you here should be matched to what you see here. This most central
that one.
region.
Okay.
Yeah.
Thanks.
Okay, that's different centrality.
Yeah, then we can also have a look at the high PT. Instead of model here, I brought the RAA of the J psi as a function of PT with the D measure and the charged particle measurement. Here, the open circle shows the D measure, and the purple shows the charged particle RAA, and the blue shows the from J psi. And what you can see here is that from the around 10 to 15 degrees, the RAA trend is actually similar to each other, somehow indicating the proton energy loss mechanism, or jet cancer, is a bit dominated than the dissociation or the regeneration system for the J side production here. And let me talk about the other direction, comparing the rapidity dependence. So here on the left side, again, the J psi RA as a function of PT, but the black shows what we measure in the mid rapidity, and the red show what we measure in the forward rapidity. And first of all, you can see that the suppression is more or less similar at the higher PT, like starting from 6 or 7 GeV. But at the low PT, you can see stronger RA increasement toward the low PT, especially for the mid rapidity measurement. This can be, but this feature is already there for even in the model calculation, indicating that the regeneration of the J psi is concentrated at the low PT at the mid rapidity, where the CC bar cross section is larger. On the right side, it's not actually the CC bar cross section, but the J psi cross section. But I just want to illustrate how it should be as a function of rapidity. So you can see that it's larger at the mid rapidity, like we already know from the phone and so on. But yeah, also experimentally we could see some hint of the CC bar production cross section.
So the statistical model does not work at forward rapidity. I don't have a phase boundary at rapidity 3.
Here you mean this?
Yeah, I mean it's a huge thing there, right?
Actually,
I mean somehow either I fit the black or I fit the blue, the red at the end of the day once I get my errors done, right? I mean I cannot fit both with the same statistical model. So how would I have to tweak the statistical model to get both the red and the black?
It's like even in the transport model, what we do is actually separate the regenerated J psi and the predominant J psi production. So, and then this contribution increased, then you could see upward. But the aim is here for the statistical heterogeneity model is to describe the low PT range, but really the regeneration is dominating.
Low PT I get, but I should be. I still have hopefully a fireball at least at 3 units of rapidity, so that I can still do my statistical game there.
But does it have the same density of CNC bar?
Well, if I have the famous phase boundary, I have always mu equals 0, so what can I change? I'm not saying that I agree with what I said, but if I assume that I have the phase boundary, then I'm led to conclude that I cannot have the red and the black points on top of each other, unless there's other stuff which is not coming out from the statistical model.
I guess the charm cross section is an input to it. The
Yeah,
primordial charm, right?
Yeah.
Oh yeah, that's right. That's correct.
Yeah.
That's correct. So the gamma charm is actually different. Okay, fair enough.
I'm sorry, what is the difference between primordial charm and gamma charm?
Same different. So you have the charm you throw into your soup is not the amount of charm if you would let the soup cook infinitely long. So it's not the thermal amount, right?
Okay.
Because you have the charm is too heavy, right? So this is so you have a gamma charm which sort of controls how many charm you really have, and this is controlled by the initial hard collisions, and not by the cooking. Charm is uncooked. At least as far
Because
as
if you cook, it goes away.
no, we have more unless you just get whatever you get the thermal amount. Right?
So when you say cook, you mean increase the temperature, you don't mean just.
No, you keep the temperature fixed forever. Then the amount of charm in the soup is determined by the temperature only.
Well, yeah,
If you have a hard collision, you produce whatever many charms, but you don't have enough time to cook them, so you have to deal
They're
with
not
these charms.
thermalized.
They are thermalized as far as
thermal production is just neglectable. Okay, it's just
exactly.
Thermal production is negligible.
Right.
It's not
Yeah.
zero, but it's small. Most of them are primordial. And if you have more, they're more likely to find each other.
And primordial, you put that in yourself.
You put
Well,
in
the
a
hard scattering puts it in for you, the initial state.
and in the thermal model, you put a factor gamma charm in front of your thermal distribution to adjust for the amount of charm you have.
So he puts it in.
Well, no, the Heidelberg.
Heidelberg
folks.
puts it in. I think you should go on.
Yeah. So what I want to show you here is that actually the model description is quite good and agree with what we measure, but still it's not conclusive yet. So here, for instance, like with the cold nuclear matter effect is not taken into account. And I'd like to discuss a bit more in the later slide with the field measurement. But let me move to the elliptic flow measurement. In the left plot, you can see the V2 of J psi as a function of PT measured at the with rapidity shown in the blue open cross, and the forward rapidity shown in the red circle. So both at the mid and the forward rapidity, we could see the positive J psi V2. And these two different curves shows the yellow and the blue shows the different transverse model. Interestingly, both models describe the low PT quite well, while fail to describe the intermediate or high PT. So it might be something that missing in the model, for instance, like the path length dependence of the energy loss or the dissociation component. But I'm happy to show you this theoretical improvement on the right side. Actually, the left side is the same plot as I showed in the previous slide, but in the better view. But the right side is the updated transverse model calculation in this spring. And the gray was the one which we saw in the left plot, the old transverse model calculation, and the green and the red shows the updated one. So as you can see that the model described far much better than before, especially above the 6 GB.
What did they add?
Yeah, exactly. So what they do is that actually for the old calculation, they use the CC bar spectrum based on the blast wave, which means that it's already normalized. But now they put the C-quark phase-based distribution as they do for the open charm simulation. So this is, which means also so-called off-equilibrium spectra. So
I have a question more for our theorists than for you. So how many additional parameters did they get to add?
I don't know how many extra data points you have.
One more than that.
Yeah, and also the green and the red difference. I'm not the expert for the transfer model, but I was really happy actually to see this plot because we had the left plot for a long time, and the green and the red difference is from the space momentum correlation between the charm quark and the high flow quark in the QGP. So it's really like the charm quark is normalized in the medium, and this V2 measurement in this intermediate PT transport this information in the V2 final V2 measurement. And let me move to side 2S. Again, sorry, this is PT, the RAA as a function of PT, and this is the J psi, what you saw before, together with side 2S, which is shown in red and the yellow in the bottom. So again, thanks to the different, the complementary, the configuration of ALICE and the CMS, we could really extend it to measure the J psi and side 2S in the wide PT range from 0 to 30 GB. And what you can see here is that the suppression of side 2S is stronger than what we see for the J psi. But still, nevertheless, the side 2S also show the trends of the increasing RAA toward the low PT, which give kind of hint of the side 2S regeneration also in the medium. But it's actually once you have side 2S and the J psi, it's better to move our observable to the ratio. For instance, here in the left plot, this is the cross-section ratio of side 2S and the J psi as a function of centrality. The advantage of this ratio is that you can, also both from the experiment and the theory, you can really cancel out many things in common. For instance, like theory side, the initial state effects like the shadowing can be cancelled out, and also the charm-quark cross-section dependence can be also cancelled out. So that's why you could see the smaller error band in this plot compared to what we saw in the RAA plot. So here as a data point, we have ALICE LED 5 dB measurement in forward rapidity together with NA50 measurement. And what you can see here is that what we measure at ALICE is that the larger ratio over the centrality and also the centrality dependence shown in NA50 is not found or is seen in the ALICE measurement. Interestingly, this in here, actually the somehow transport model described what we measured a bit better. Also the trend of the small dependence in the centrality, while the statistical heterogeneization model underestimate the data in the, especially at the most central collision region.
Looks like it has a terrible agreement with the Alice data.
Well, if they just fitted the wrong data, it fits perfect
Yeah.
with the NA49, right?
What I can, so.
I have a quick question here. So is it expected that like from an A50 that's like 17 GeV energy to the like Alice data's 5 TeV, but the ratio difference is not too big? Is it expected that there's such weak energy dependence?
Yeah, actually it's a good question. I actually didn't see the model calculation for the NA50. So I think it's good to check. Yeah, thank you.
Well, if you have a quark-gluon plasma in both cases, then you should be roughly the same, right?
Well, but does the recombination feed them at the same rate? No.
Why?
Well,
Learning energy is
If you
different.
think about statistical naturalization model, I mean, the gamma factor is out because I take the ratio, right? So at least there, I don't know.
No, but you're close enough, at least for that 17 Jeff, you're very close to threshold. So the extra mass does make a difference.
Mass for what?
Well, the psi prime being heavier than the J psi.
But the temperature, what are the spectra? Are they so much harder there
At Alice, yes.
for the
Yeah.
charm? Yeah.
Oh, yeah, a lot. That's probably the answer.
So then we move to bottomonium production. The left plot, you can see many kind of lines. I don't want to go through detail, but compilation of different experiment. The reddish color shows the epsilon 1s measurement, and the blue shows the epsilon 2s, and the green shows epsilon 3s, which could be only accessible by the CMS so far. And this different excited state epsilon family has different sensitivity to the medium since the binding energies are different, as you can see here. And by eye, you can clearly see that suppression, first of all the species, the stronger suppression toward the central collision, and you could see nice sequential mating pattern is that the 3s suppress more than the 2s, and 2s more than the 1s. So is it then the fully understand as explained by the what we know as a sequential mating scenario? Actually, it's not that easy, so cannot conclude that the bottomonium is the thermometer yet, because we have to consider several things like the feed down effect, for instance. Especially for the epsilon sector or the bottomonium sector, we don't have knowledge about the p-wave state decaying into the excited epsilon, which is not measured even in the PP. So this is also increased the difficulty of interpreting this result. And though it's small, but the regeneration contribution, we should understand a bit more. And of course, the core nuclear matter effect can also play a role for this behavior.
Can I ask a question about the feed down?
Mhm.
Do you or does anybody think about feed down from exotic states like the XYZ states?
Yeah.
Are there enough of them to matter?
That was my question.
I don't think so, because we just start measuring X38, 72, so I don't think so. But mainly for this S state, at least we know a bit better. So mainly, but still the P wave is not accessible for them.
Sorry, does feed down just mean decay?
Yeah,
Thank
right.
you, thank you.
So there are different models in the market for the bottomonium production. For instance, the co-mover model in the left side and the hydrodynamics. These are actually these two models interesting because co-mover doesn't really specify that your co-moving medium should be the QGP or not. And also hydrodynamics, I think they don't even assume the kind of QGP structure what we know. So, but nevertheless, they capture the data trend quite well for the epsilon 1s and also for the 2s.
I thought in Coulomb calculation, they use a cross-section. Cross-section is different to GP or in hadron Collider. That's how they differentiate the properties.
Yeah, right. Right, you're right, right. And yeah, but all the interaction of the medium is more how to say more considered for inside the transport model. As you can see on the right side, they also fairly describe the measurement quite well. But here what you can see is the last uncertainty in the all theoretical calculation. The all of models suffer heavily for the uncertainty from the NPDF effect, and also the co-mover include the uncertainty of feed down, which actually the rest of the model doesn't consider any the uncertainty for that. But so it's really hard to rule out any single model so far, but still we have chance again with this ratio plot. It's a bit more complicated than what we saw before for the charmonium. This is double ratio of this epsilon 3s to 2s divided by the in the let to the PP. So green shows the resulting measurement, and the different color shows the model prediction. So for instance, like Boltzmann equation description, which described quite well the RAA, completely failed to describe this ratio plot. And also this co-mover underestimate, and yeah, the rest. It's really hard to say since the uncertainty of the measurement is quite large, and also we can clearly see that
They're all wrong.
but also difficult to say the Boltzmann, I would say, under this calculation
It's more wrong.
But what is also interesting here is the right side, the statistical harmonization model calculation. Actually, it's not drawn together, but if you compare by eye, then you can see the trend is quite well described by the statistical heterogeneization model. This is also interesting because the statistical heterogeneization model basically assumes the kind of sufficient CC bar or BB bar cross section, but here even for the BB bar it works quite well. So
It does a pretty high momentum. Right, PT is less than 30 JeV. So
yeah, but from
are they
starting
all one?
it's starting from 0, so basically it's still dominated at the low speed.
What's the OQS plus PNRQC? The orange.
Orange OQ. Open quantum system. It's this old description of QQ bar, which inherited from this Schrödinger type description, but in the open quantum system, so that you put the spectral function and you just let this QQ bar evolve inside the system. So it's a bit improvement of this classical QQ bar description.
So that has the smallest effect of the medium, right?
Yes, I think the parameter is a bit simple here. Basically, mainly, or it's dominated by the temperature.
So what PT cut is this data for the charmonium? I don't see. Oh, now I see. But what is their acceptance? Where do they see this stuff? That's certainly not a 0, right? I mean,
it's
not a 30.
It's
right. So that's why I mean they don't have uniform acceptance, do they? Or are they correcting for it?
Yeah, we correct for that.
Oh, that's corrected. Okay. Good.
Yeah, and the last thing I want to show in LED is epsilon 1 as elliptic flow. So in the left plot, you can see the V2 as a function of PT, and you can see the data points here that there's no evidence for the finite epsilon 1s V2 over measured PT, and which was actually already shown in the Alice measurement as well. So there are different models, like 5 models, and it's tricky because anyway, the uncertainty of data is quite large. So actually, I don't want to say anything, but
They're all
everything
right.
is possible. But but nevertheless, yeah, the CMS at least claim that the results are consistent with the different model prediction. But we have to understand a bit more on the epsilon in general because it's too heavy. So on the right side, you can see the beta value for each particle species as a function of PT. So for the epsilon sector, which is shown in the pink or the red, that even for the 10 GeV that they have 0.5 or something, which means they are so slow because they're heavy. So which means that the low PT, the epsilon cannot escape the QGP, so it cannot be delivered, this initial geometry information. And intermediate PT, the turbo distance or the path length can be varied easily depending on the shape. So the net V2 can be also the negative or the positive, so it's not easy to interpret. So what is actually what the V2, which deliver the similar message as we get from the light flavor or the D-measure, would be the high PT epsilon. So, and this is reason why actually in here, the blast wave-based calculation also show large deviation around the 10, starting from the 10 GeV. So the physics message here it's not easy, but I think I really hope that the better precision measurement at the high PT starting from 10 GeV with more granular binning would be a bit interesting. I think one can reach in the 1-3 measurement in either CMS or ALICE. So let me move to the PLED. So I already mentioned several times about the cold nuclear matter effect. So what is it? So depending on who talk about it, they sometimes define it slightly different way, but I'd like to define the cold nuclear matter effect as the effect present in the heavy ion collision, except for the QGP effect. So which includes the classical nuclear modification of Proton distribution function as a function of Bjorken X, as you can see in the left plot, and also the saturation of in the colorless condensate approach, which is due to the extremely high gluon density at low X range. And also there's a possible multiple scattering, and there's a consequences you could see the energy loss, but in the different pattern depending on coherent or incoherent, and also in the depending on the multiplicity later state or the final state, you can see the breakup by the Kolmogel as well. So, and also this on the right side, you can see the coverage of the different 4 main detector at the LHC as a function of X and the Q square. So we could cover from minus 10 to the 5 to minus 10 to the minus 1 in the different Q square values. So it's the LHC provides actually nice test bed for the cold nuclear matter effect as well. But before going to the measurement, this actually this is slightly different than what is in there, but I just want to highlight what we did as LHC did for the NPDF study. Here I present the NPDF and next leading order, so-called NCTEC and the EPPS16 the PDF set. And on the left side, you can see the effect of this NPDF for the prom-J size measurement, and the red box shows the purely from the original NPDF set, while the blue, which has reduced uncertainty box, shows the reweighted NPDF set based on the LHC measurement. As you can see here, we really improved a lot on the uncertainty where we are interested based on our measurement. And this could be done a bit more in the recent paper. On the right side, this was mainly done with NCTEC 15, and all the plots shows the ratio of the lead and the proton PDF for the different quark content and the gluon here. And what you can see here is that the different colors. So black shows the original NCTEC 15, and the blue include the vector boson production for the constraining the PDF set. The green shows the vector measured and also the inclusive hadron production. And the red is really the latest one, including the quarkonium and the open heavy flavor measurement. So especially in the gluon distribution, you could see the error band gets really narrower once we add this recent LHC measurement as an input for the NPDF. So this is, I just want to advertise how it is. But let me go to the JSI RP LED first here. On the left side, you can see the RP LED as a function of rapidity measured at least for the mid rapidity and the forward and the backward rapidity from the LHCb. Even from the data, you could see the rapidity dependent modification for the JSI production in PLED. And the trend is quite well described by different models, including the NPDF set.
How is the prompt shape psi defined?
Prompt JSI is the JSI which is produced directly as a JSI and also feed out from the excited state. Everything but not from the B hadron.
Oh, but not fed down from any B.
Right.
Okay.
Yeah.
But whether they have medium modifications or not, you don't know, right? I mean, final state interactions, you cannot tell. I'm wondering how you can get NPDFs out of the shape psi measurement if the shape psi, you have your co-mover and whatever.
Yeah, exactly.
Yeah, how do you do that?
Actually, this was done by these people here, for instance, Landsberg and this Mr. group.
Yes.
Does that. What they do is, for instance, Landsberg, they really reweight the component to match to what they actually measured at the LHCb.
Also in PLED, right?
Right.
But then how do you remove meta effects when you want to
have some constraint evolution
Look,
constraints, right?
Yeah, but I have this boring final state, I call this old-fashioned final state interactions, which is in there. And so I need to remove this to say something about PDFs, right?
So can I make a comment?
Yeah, sure.
So there's been a lot of back and forth about that because I think about it exactly the way you do, right? There's what's in the nucleus
Yes.
that's just sitting there, and then you hit it with the probe and you have some initial and final state interactions. But some of these guys wrap what we would call final state interactions
In the PDF, in the fragmentation functions or whatever.
And it's not all of it, I think, because when they do the fits, they also have some constraints of the PDFs from QCD evolution. So I think they take some of it.
Yeah, I also agree. Actually, I agree that somehow all these effects are encapsulated into the NPDF. They are modified in NPDF. So,
right, and it bugs me because to me it seems that a PDF should not depend on the probe, right?
Yeah, right.
But I think some of these do, and I don't know about those fits.
Yeah, it's more or less similar for the free weight.
Isn't there something where, was one of the things it's quite different if you look, depending on what frame of reference you look at it. Like if you look at a nucleus as a flat pancake, and the particles coming through, basically it's, everything there is part of the nucleus. But then if you go to the rest frame of the nucleus, you have your probe coming in and it interacts here and here and here, and somehow those interactions are separated.
Yeah.
And in fact, if you have like a exchange of gluon here and exchange of gluon here, then you also need to exchange another gluon to preserve color in different parts. And so somehow they are obviously the same description of the same thing in different frames of references, but what seems like it's part of the picture and what doesn't depends on the frame of reference.
Yeah, but if I put this in the NPDF, what is there left for the cold matter effects? It's all in the NPDF.
Not all of them.
Why not? How do I separate it?
Well, the thing that bothers me is, so if I come along and measure photons, right? That should, the PDF is one of the terms in the probability of finding a photon. And it seems to me that shouldn't depend on the reference frame either, but yeah, I don't know.
All right, anyway.
Yeah.
This reference frame has always bothered me also.
Physics by Lorentz transformation.
Yeah, and on the right side, as an example, I also brought the same RP-LED as a function of PT, and as you can see here, the suppression or the modification is concentrated low PT, which is also described by the models, including the NPDF, and also not. So I think it's not as simple as we know, but still we can
But
move.
before you move on, it seems to me that right-hand plot answers Volker's question, because not everything is in the PDFs, right?
Yeah, right.
But how do I separate whatever the good from the bad, right? I mean,
No, actually, this
Which
I
is
think
good,
this.
which is bad.
well, that depends on the reference frame, right? For some people, the good is the NPDF. For other people, the cold matter effect is the good. But I mean, you still need to separate it. I mean, I don't know. Anyway.
That's why we need an electron-ion collider.
Maybe I will confuse.
When you
Yeah,
change
yeah.
you still get your final state directions. The electron-ion collider only takes care of the initial state directions to some extent, right?
Yeah, which is a simple probe.
Yes.
Maybe I will bother work more in this measurement, which shows the excited charmonium state in the PLED, which shows the side 2s and the J side. So here, for instance, like here, you can clearly see that the difference for this, a different modification for the side 2s and the J side and the backward rapidity. So
By the way, Phoenix saw the same thing. And it used that's what got me all bothered about this, because if it's an initial state effect, how does the QQ bar know, how did the CNC bar know if it's gonna end up as a J psi or a psi prime?
Yeah. Yeah, right.
Your question is valid if only considered as incoherent. It's coherent effect.
Yeah, but maybe I can do, if I did coherence, I could sort this out experimentally, I'm good with you, but I mean, that's why I hope that my question about the prompt shape psi would answer my question, that this is some special shape psi which comes with a little marker, and then I know these are the guys which I should look at, right? But apparently it's not so trivial.
This energy formation time jet psi already covered on this coherent this energy.
Is that true at RHIC energy also?
RHIC is, I vaguely remember as of the boundary.
So you are saying I don't have final state interaction with these energies?
I did not. I say it is coherent effect.
He says you can't, no, I mean, he
You
says,
don't
yeah,
separate.
he says you can't tell, it's a
Cannot
digital.
tell. Cannot tell.
Okay,
Yeah, but
let's
but
call it goulash. Gumbo, everything goes in.
No, that's not fair, that's not fair, coherent effect is.
No,
that's
but I mean,
real.
the separation of what comb, the matter effects and NPDF, I think, I don't know, anyway.
I mean, we think of it incoherently, that would be the problem.
PDF is coherent potential. That's how I think.
We should let our speaker tell us
Well,
what
that's
she
not-
thinks.
yeah, here. So like we just discussed about the initial state effect, including the NPDF or the coherent energy loss. They shouldn't be largely depend on the specific charmonium measurement, as we know. So this is, for instance, like here in the models, they don't assume anything but the initial state effect, so that there's no different description for the side 2s. So it should be actually identical. But in the right side, you can see the models, including the core mover picture. So for instance, like the forward rapidity, where CGC calculation is available, you could see the difference here for the side 2s and the J side. And also the core mover model describe this backward discrepancy between the side 2s and the J side here quite well now.
So which side is the lead nucleus in your, is it on the right or on the left?
This is lead going direction and then
Okay,
this peak going
okay.
direction. Yeah, so from this point of view, actually, that we somehow have to really seriously consider the final state effect actually in the PLED system as well. And this could be also studied in the different state, like the LHCb, they could firstly measure the chi-C1 and chi-C2 in the PLED collision, As you can see in the left plot, they measure the chi-c decaying to the J-psi and the gamma, and they could reconstruct the mass difference using the proof to fit the chi-c1 and the C2 signal, as you can see here. What is interesting is that this chi-c state, the mass is larger than the J-psi, but smaller than the J-psi, the psi2s. And the mass difference between these two states is about 50 MeV. So maybe this measurement can also explain what's between here, and it's related to the mass or not. This could be the original idea of this measurement. But on the right side, you can see the cross-section ratio for the chi-c2 over chi-c1. And with an uncertainty, actually, we cannot say it's that much, but yeah, the same cold nuclear matter effect for the chi-c1 and chi-c2 at the forward rapidity and the backward rapidity. So yeah, but this increase with increased statistics in 1-3, maybe one can see a bit more, yeah, out of this measurement. And let me move to the bottomonium sector. On the left side, you can see the RP-LED and the RAA of Upsilon family, the 1s, 2s, and 3s, with the RAA in the blue and the RP-LED in the red. Here, what you can see is this, again, the sequential suppression pattern, even in the P-LED. Though the size of the suppression is much smaller than what we see in the RAA, there is some trend. But if I see into more differential way, like the rapidity distribution for low PT and the high PT on the right side, this suppression pattern, this only depends on the backward for the low PT only, but it gives somehow similar level of the suppression in the other arms. And also, what is important is that the suppression level is not as much as what we saw in the RAA.
I think the middle one and the right one are within statistics in excellent agreement.
Yeah, so this is the only, I think this range is only interesting.
Yeah, but you have no, you don't have a significant difference between the green on the left, in the middle, and the green on the right.
Yeah. But still, if for this information into as a function of RP-LED for each species and combined with the model prediction, including the co-mover breakup contribution, actually the RP-LED of all states well described by this model. And also different suppression level is expected as what we saw in the excited charmonium, like Psi2s. But I just want to address another possibility, and on the right side, it also shows the RP-LED of Upsilon 1s in the upper plot and the 2s on the bottom plot as a function of rapidity. And the data points show what we measure at the LHC and ALICE. And the blue shows the model including the cold nuclear matter effect only, but the red shows on top of that adding the QCP effect. And interestingly, actually the red band from the theory described quite well the measurement compared to what to the one he only considered cold nuclear matter effect. So it's one model. So, but what I want to address here is that still many things, it's still open question. So we have definitely go to the vector precision measurement to somehow rule out possibility of several model prediction. And maybe slightly connect to the mini QCP in the P-LED. We can also have a look on the Quarkonium V2 in the P-LED and also PP. The left side, you can see the J-psi V2 as a function of PP. The red shows what it was measured the LED, blue shows the P-LED, and the green shows the PP. So green, we are happy since it's 0, what we expected PP, but I just want to show the sizable V2 in the P-LED measurement, which is not reproduced even with the transport model, including the final state effect, especially at high PT. So this is, this is still not clear, and also give us the question for the round 3. And similar measurement was also performed for the upsilon 1s. And as we saw already in the LED, it's close to 0, or yeah, there's no hint of non-zero value also in the PLED, as you can see in the right side. But still, this considering the uncertainty, that we cannot say a lot, but expecting better precision measurement in 1C. So yeah, so let me go to the PP. What the main motivation or the main goal of the measurement in PP is having the reference for the PLED and LED measurement, as you could see in the formula of our PLED. And as you can see in the bottom plot, we achieve already really good reference covering the wide kinematic range, and all measurements from the different experiments agree with each other nicely, and the uncertainty is small enough to calculate our PLED and RLAA. And also the other motivation of studying in the PP is understand the production mechanism. For instance, like charmonium that include the perturbative and non-perturbative feature of the QCD. So it's important to understand how it is by measuring, precisely measure the different state of the charmonium and the bottomonium. And for this goal, actually, in my point of view, we already did good job. In the middle plot, you can see the cross-section measurement in the PP as a function of PT. And the red dot shows the data, and the different curve shows the theoretical calculation. And here in the bottom, as you can see, the uncertainty of measurement is far smaller than what we have in the model. So we really provide a nice reference for the theoretical development into this direction. So I can, of course, show tons of this plot in PP 2.76 TeV to 13 TeV, but I don't want to repeat anything. But I just want to show some production in PP, especially the production associated with event property, which gives kind of interplay between the hard and soft particle production, possibly connect to the collectivity. So here, this is the J psi production as a function of multiplicity in PP. And in the left side shows what we measure in the forward rapidity in ALICE, 5 and 13 TeV. And the right side shows what we measure at 13 TeV in mid rapidity. So while this distribution is linear for the forward rapidity, what bothers me and also this community was that it's at mid rapidity, it goes increase faster than linear development. But the feature is already captured by the theoretical prediction. So there actually was 2020, even before we discussed a lot about this plot, like maybe it's due to the autocorrelation of the mid rapidity that the track comes together. That's contribute a lot on the multiplicity and so on, but we could rule out, since we could estimate the multiplicity with the visual detector on the far away, and we could also obtain the similar trend for there. So it's not I just want to emphasize that it's not the autocorrelation anymore. But what is interesting is that actually the trend is well described by the different model originating from the different physics mechanism. For instance, like PCA includes the MPI effect, actually quite nicely described, and the EPOS 3 is based on hydro, and it expects the saturation of the soft particle production in this kinematics and so on. So it's one thing we can get some idea about the underlying event and the hard proof production. And similar study could be also done with bottomonium sector, the CMS. On the left side, you can see the upsilon S over upsilon 1s as a function of multiplicity. And you could see some universality for the PP and PLED, showing the similar trend of this cross-section ratio for the 2s and also the 3s. This could be also look into more detail by more differential analysis, like here as an example. Here, what they did was actually split the azimuthal area into the three sections, like the one close to the upsilon momentum direction and the transverse to the one to the transverse to the momentum and the backward. What is interesting here is that it somehow show really similar trend for all different configurations, which means that the upsilon production is really connected to the underlying event rather than it produced as a really hot, fast hot group irrelevant of underlying event.
I have a question here, like, so the definition of the delta phi is with respect to the track momentum direction. What is this? What track is that?
This track is the track which you use for the x-axis number of track.
If there are multiple tracks, then
here it's not the correlation between this track and the upsilon reconstructed upsilon, but we calculate number of track in this each color. Like in the green, we count how many tracks inside there, and define as a kind of partial multiplicity or the multiplicity.
So it's sort of like an event plane.
Yeah, exactly. And the other thing I want to show you is the J-psi production in the jet. This was firstly measured at the LHC and the PP. So what they measured was the momentum fraction distribution of the J-psi inside the jet. So the blue shows what we measure and the data, and the red shows the model calculation. For instance, like NRQCD here. And here what you can see is that the measured data show far more jet activity, which means the spreading over the jet than what we expect from the NRQCD prediction. And this trend was described only after adding this leading order fragmentation function to the LDME based calculation for the J-psi production, which tells us that at least high PT J-psi produced at the later stage of the parton shower, really in the jet. So it tells us that the jet quenching contribution should be also considered to interpret the AA measurement. And yeah, so actually the CMS also measured this J-psi in jet in Large Hadron Collider. So you can find the reference here.
Do you know if there's like a E plus E minus baseline for that measurement? Like, did they do it at LEP, for example, J-psi in jet?
E plus minus, I don't
Maybe
know.
Answer is no. So we'll hear you Thursday.
Yeah, and actually, can I continue or not?
You can continue.
Yeah.
Disappear one by one.
Because from now on,
I suggest you finish in 5 minutes.
yeah, because from now on, I'd like to show slightly different topics, which is, for instance, it's the observables which use the J-psi as a tool.
This is what I was mentioning earlier.
Yeah.
Sorry.
So here, so this is about this photo production.
Oh, yeah, okay.
So here on the left side, you can see the RAA of J-psi as a function of centrality for different momentum. So red shows the J-psi momentum smaller than 0.3. And the blue shows the one between 0.3 to 1, and the black shows 1 to 2. And what you can see here is really large excess of the yield in the low PT J-psi and the almost peripheral collision. And this was actually first measured at the LHC in 2016, and it was not conclusive yet, but it could people claim or its possible explanation was coherent J-psi photo production in the peripheral collision. So now we measure this red contribution, and this defined as a coherent J-psi production, and we could draw the cross section as a function of centrality, as you can see in the right. And this could be also compared with the photo production models describing the photo production, mainly works for the UPC in these different models here. But in order to describe what's in the peripheral collision, the models, all of these models in the UPC are slightly modified. For instance, the VDM, they set the limit of the impact, they modify the impact parameter calculation, and as this GBW, they exclude the production, photo production in the overlap range, but calculate as it is in the UPC. And also S2 and S3 is just different scheme how they handle this overlap region. But as you can see here, actually in general, with an uncertainty, the models quite nicely describe the cross-section what we measure. So it gets more conclusive that what we see here is the coherent J-side photo production, even in Large. This is actually really interesting because how can they survive from the QCP and still contribute a lot in the yield? This could be a bit this also, I think this is also a nice measurement from the LHC, which also clearly shows the different production contribution for the J psi using this log PT, one observable with respect related to the PT. One could really fit the photo produced J psi and the hadron production contribution in this plane, so that and also statistics law, so that they could really measure this cross section of the photo production as a function of PT, which is highly connected to the T here. So so I don't know who can decide. From now on we agree, but for me it's really like the photo production. So which will be really useful information for the gluon density and the shadowing together with UPC input. And still, for me, it's very interesting as how they survive and how then can they also solve the information of the QGP that they see or not. This would be interesting question about this topic. And the other thing I want to show you is polarization measurement. We already measured the J psi and epsilon modulus polarization in LED, in helicity and Konigshofer frame, but here the recent paper shows what we measure with the event plane. It gets really interesting because this event plane is perpendicular to the magnetic field and the vorticity, so that, and also together with the shock formation of the heavy quark, that it can deliver this initial information to the detector. In the end, we measure. So here the polarization was measured as a function of centrality, and you could see this small like 0.2, but the significant polarization, especially in this 40 to 60 centrality class. And this is similar conclusion as we could obtain already from the light flavor sector from the phi measurement. But the question is still this in this now the turn its theoretical interpretation is a theoretical a community should react, because we don't know yet still if it's applicable of the description or the interpretation what was done for the phi measurement is also valid for the J psi or not. So this is, but if so, then it will be also good proof to understand a bit about this initial state of magnetic field and field. And then really the last, I'd like to show the P sub C and the X3872 measurement, which is new in LED. So why I brought this? So P sub C could be measured by the J psi decay, the P sub C decaying to J psi, muon, and the muon neutrino. And its momentum could be reconstructed based on the J psi and the muon, as you can see. And as you can see, the quark content of the P sub C is P quark and the C quark is somewhere. It can be the bridge between the charmonium and the bottomonium, though the kinematic would be different. And the other new thing is X3872, which is also interesting proof, also for the particle physicist, I guess. It could be measured by J psi and the pi, as you can see here. And in medium, for instance, like breakup with the core mover. or the regeneration is sensitive depending on how the inner structure of this X3872 is. So this is still, we just measured, so we have only 1 point here. And yeah, but at least we could confirm that it's there. So I think with increased statistics, it would be also interesting to go into this direction, also together with other exotic methods. So today I try to illustrate you what we did at the LHC last year. So we could get the higher precision, more differential measurement in the old collision system, and we could see some new observables, which was in the Quarkonium sector. So we could see the suppression and the regeneration based role, but for the charm sector, we could see the strong hint of the charm quark harmonization in the QGP. And the P-length excited state measurement clearly show there is something more than the initial state effect what we know so far. So this will be one take-home message for you. And the PP collision, it's not just the reference, but it could provide further understanding for the production mechanism and also connection to the underlying events. But last but the least, the 1-3 is ongoing. So, and the data will be coming next year. So, and we expect much larger data sample. And in our list, especially, we equipped the new vortex detector and the new GEM readout and TPC. So I hope we get the more statistics with better resolution, giving the more precise measurements in the future. Thank you.
Thank you very much. Very nice, comprehensive talk. Lots of materials, and many questions already asked. Any other question or comments? I have a comment about the polarization measurement. I think the phi theory is already not correct. So here we should not rely on that, especially this reference to protein. So I don't see that is validity of that theory paper. They said there's a special phi field in the collision. So I'm not sure that is the right.
Yeah, but this is again what we measured, but I think it's really difficult. And how do we know what really the contribution from the magnetic fields and the angular momentum? How can we really distinguish between these two effects?
So in which direction does the spin of the shape psi point from your measurement that I missed?
So here the theta is defined as the polar angle emission of the positively charged decay lepton, in this case mu1, with respect to the event plane. I'm really poor in this geometry, so I couldn't draw the picture.
Xingyan, you have a comment or question?
Yes, I'm just asking, if you compare to, I mean, if you look at the phi meson, for example, the polarization, they also have some kind of angle, azimuth angle dependence respect to the event plan. And maybe I'm just wondering whether maybe you can also look at that too in this measurement.
This measurement already is with respect to event plan, I think.
I don't know. I think I'm saying that the dependence, the polarization as we actually predicted that is not zero, perpendicular to the event plan. Okay. In fact, the polarization, at least to explain the phi meson polarization, in fact, it has nothing to do with the vorticity. So the event plan dependence is purely because of the V2 of the spectrum. So maybe I'm just wondering whether one can also look at your J-psi polarization, the angular dependence.
Yeah.
Any other comment online? Offline?
I have one question, no? So
Go ahead. Ashish.
on this plot, Minjung, so what's the reason for choosing the forward rapidity? Is the measurement carried at mid rapidity?
No, it's only because at least we have the mid rapidity, the central barrier detector at mid rapidity, and we have the muon in the forward rapidity. And the actually data taking scheme is a bit different, so that we have larger statistics in the muon, so that we have enough statistics in the forward rapidity to measure this. So not a really physics-oriented decision to measure at the forward rapidity, I would say.
I see. Okay, thank you.
Any other question or comment? If not, let's thank the, yeah, go ahead.
Yeah, very nice talk. So I just have a question that, for the next set of data coming in with the higher statistics, what would be the most interesting measurement for us to see that we're resolve some issues? And of course, if you have thought about S-Phoenix also, because that's what we are interested in. So what will be S-Phoenix can help us resolve some of the issues?
She's from Alice.
If I may, then actually I'm looking forward to seeing the data from S-Phoenix. I don't know in detail, but somehow it's like it will be the epsilon factory at the RHIC, this S-Phoenix, so that I think it's good to have the excited state epsilon, precise measurement of the excited epsilon would be interesting to see with better precision and more granular than what we already have at the start for the Phoenix. I don't know. Start. This will be interesting.
Okay, so let's thank Minjung one more time. Thursday we have an in-person seminar by Henry, so please come. Thank you all for coming. See you on Thursday. Goodbye.
Bye.